myself Ankush Haldkar. This course is based on safety in typical civil structures. Safety in typical civil structure is of paramount importance to protect the lives of occupants and the integrity of the building itself. Here are some key aspects of safety in typical structures. Structural integrity. The structural design and construction of civil structure must adhere to building codes and standards to ensure they can withstand various loads including dead loads, the weight of structure itself, live loads, people and furniture, and environmental loads, wind, snow, earthquakes. Engineering use materials like steel, concrete and timber to achieve the required strength and stability. Structural integrity refers to the ability of a structure to withstand various loads, forces and environmental conditions without experiencing significant deformation, damage or failure. It is a fundamental concept in civil engineering and construction, ensuring that building, bridges, dams and other structures remain safe and functional throughout their intended lifespan. Here are some key aspects of structural integrity. Load bearing capacity. Structural integrity involves designing and constructing a building or structure with the strength and load bearing capacity necessary to support the expected loads. These loads include dead loads, the weight of the structure itself, live loads, people, furniture, equipments and environmental loads such as wind, snow and earthquakes. Materials and construction. The choice of materials, construction techniques and quality control during construction are crucial for achieving structural integrity. Common construction materials include concrete, steel, wood, masonry, each with its own properties and applications. Design standards and codes. Engineers follow established design standards and building codes to ensure that structure meet minimum safety requirements. These codes specify factors such as material strength, load limits, foundation design and safety margins. Stress analysis. Structural engineers perform stress analysis to evaluate how different loads and forces affect the various components of a structure. This analysis helps determine the size and shape of the structural elements to ensure they can withstand these forces without failure. Safety factors. Engineers apply safety factors to design loads and materials properties to account for uncertainties and unexpected conditions. These factors ensure that the structure have a margin of safety beyond the expected loads, helping to prevent catastrophic failures. Foundations. A solid foundation is critical for structural integrity. Engineers must consider soil conditions, bearing capacity and settlement rates when designing foundations to prevent settlement or tilting of the structure. Regular inspection. Periodic inspections and maintenance are essential to monitor the ongoing structural integrity of a building or infrastructure. These inspections can identify issues like corrosion, cracks or other signs of deterioration and may compromise safety. Environmental factors. Structural integrity takes into account environmental factors such as temperature changes, moisture and chemical exposure. Protective coatings, insulation and corrosion resistant materials are used to mitigate environmental safety effects. Seismic and wind resistance. In regions prone to earthquakes or strong winds, engineers must design structures to be resistant to these forces. This may involve the use of seismic bracings, flexible materials or reinforcement to prevent collapse during seismic events or high winds. Local distribution. Structural integrity also includes the proper distribution of loads throughout the structure. This ensures that loads are transferred from one component to another efficiently, reducing the risk of localized failures. Fatigue resistance. Structures are subjected to repeated loading over time. Engineers consider fatigue resistance to ensure that materials and connection can withstand cyclic loading without developing cracks or other weakness. Testing and quality control. During construction, materials and components are often tested for quality and compliance with specifications. That ensures that materials used in the structure meet the required standards. In summary, structural integrity is a fundamental aspect of civil engineering and construction, aiming to create safe and durable structures. It involves careful design, appropriate materials, adherence to codes and standards, and ongoing maintenance to ensure that a structure can withstand its intended loads and environmental conditions while providing long-term safety and functionality. Foundations. Proper foundation design is essential to distribute the building load safely to the ground. Factors like soil type, bearing capacity and groundwater levels must be considered to prevent settlement or foundation failure. Foundations are critical components of civil structures, serving as the base upon which building, bridges or other infrastructure are constructed. Their primary function is to transfer the loads from the structure to the ground in a stable and safe manner. Foundations play a crucial role in ensuring that structural integrity and longevity of the entire civil structure. Here are some key aspects of foundation in civil structures. Number 1, load distribution. Foundations distribute the weight of the structure and the applied loads such as occupants, furniture and equipment evenly across the underlying soil or bedrock. This prevents excessive settlement or differential settlement, which can lead to structural damage. Types of foundations. There are several types of foundations used in civil engineering, including shallow foundations. These are located close to the ground surface and transfer load directly to the soil. Common types include spread footing, slab on grade foundations and mat foundations. Deep foundations. These extend deep into the ground to reach stable soil or bedrock. Common types include driven piles, drilled piers, caissons and helical piles. Deep foundations are used when the soil near the surface is not suitable for supporting the structure loads. Soil investigation. Before designing a foundation, engineers conduct thorough soil investigation to determine soil's properties, including its type, bearing capacity, settlement characteristics and groundwater levels. This information is critical in selecting the appropriate foundation type. Bearing capacity. The bearing capacity of the soil or bedrock is a key consideration in foundation design. It represents the maximum load the foundation can safely support without causing excessive settlement or failure. Engineers design foundation with safety factors to ensure they can withstand the expected loads. Foundation design. Foundation design involves selecting the appropriate type of foundation, determining its size and shape, and specifying the materials to be used. Factors such as the structure weight, the type of soil, and local building codes and standards are considered in the design process. Construction materials. Foundations are typically constructed using materials such as concrete, reinforced concrete, steel or wood, depending on the specific requirements and local building practices. Foundation construction. The construction of foundation involves excavation, the placement of reinforcing materials such as rebar in concrete foundation, pouring of concrete and curing. Proper construction techniques are crucial to ensure the foundation strength and durability. Waterproofing and drainage. Foundations may incorporate waterproofing measures to prevent water intrusion into basement or crawl spaces. Drainage systems such as perimeter drains and sump pumps are often installed to manage groundwater and prevent damage due to moisture. Foundation settlement monitoring. Engineers may implement settlement monitoring system to track any settlement of the foundation over time. This allows for early detection of potential issues and allows for necessary adjustments or repairs. Foundation repair and retrofit. In cases where a foundation experiences settlement, cracking or other issues, foundation repair or retrofitting techniques may be employed to restore its stability and integrity. Environmental considerations. In some cases, foundation must be designed to account for environmental factors such as seismic forces, in earthquake prone regions or frost heave in cold climates. Maintenance. Regular maintenance of foundations is essential to address any sign of deterioration, cracks or settlements. Timely maintenance can help prevent structural problems and costly repairs. In summary, foundations are a critical element in civil structures, providing the necessary support and stability to ensure the safety and longevity of building and infrastructure. Proper foundation design, construction and maintenance are essential to ensure that the structure can safely withstand the loads and environmental conditions they are subjected to. Next is fire safety. Fire safety. Civil structure should incorporate fire resistant materials and design to minimize the risk of fire spreading. This includes fire rated walls and doors, sprinkler systems, smoke detectors and well maintained evacuation routes. Seismic safety. In earthquake prone areas, structure must be designed to withstand seismic forces. This includes the use of seismic resistant construction techniques such as reinforced concrete frames and base isolators to minimize damage during an earthquake. Seismic safety in civil structures refer to the measures and strategies implemented to design, construct and retrofit building and infrastructure to withstand the forces generated by earthquakes. Earthquakes can cause severe damage to structures, leading to loss of life, property damage and economic disruption. Seismic safety practices aim to mitigate these risks and ensure the structural integrity and safety of building during seismic events. These are key aspects of seismic safety in civil structures. Seismic design codes and standards. Engineers and architects follow seismic design codes and standards that are established by local building authorities and organizations like International Building Code (IBC) in the United States. These codes provide guidelines for seismic resistant design and construction. Site selection and soil analysis. Before construction, through site evaluation is conducted to assess the geological and geotechnical characteristics of the location. Soil type, bearing capacity and seismic hazard assessment are essential to determine the appropriate foundation design and seismic forces the structure may encounter. Seismic hazard assessment. Engineers perform seismic hazard assessment to predict the level of ground motion the structure is likely to experience during an earthquake. This assessment considers historical earthquake data, fault lines and local geological conditions. Base isolation. Base isolation systems are used in some structures to decouple the building from the ground motion during an earthquake. This reduces the transfer of seismic forces to the structure and minimizes damage. Damping systems. Damping systems such as tuned mass dampers and viscous dampers are incorporated into building to dissipate seismic energy and reduce structural vibrations. Reinforced concrete and steel. Seismic resistance construction often involves the use of reinforced concrete and steel, which can better withstand seismic forces and provide flexibility. Shear wall and bracing. Buildings are equipped with shear walls, bracings or structural cores to enhance lateral stiffness and resistance to earthquake forces. Flexible building design. Certain building features such as expansion joints, flexible connections and moment resistant frames allow structures to flex and absorb seismic energy. Retrofitting. Older buildings that were not originally designed to withstand earthquakes may undergo seismic retrofittings to improve their resilience. This can involve adding additional structural elements, strengthening existing ones or upgrading foundations. Emergency evacuation plans. Buildings should have well defined emergency evacuation plans in place, including safe exit routes and assembly areas for occupants in the event of an earthquake. Non-structural component safety. In addition to the structural aspects, non-structural components, example, ceiling, lighting fixtures, HVAC systems, should be secured to prevent them from becoming hazardous during an earthquake. Seismic monitoring and early warning systems. Seismic monitoring are used to detect earthquake activity, and early warning systems can provide advanced notice of impending earthquakes, allow occupants to take protective actions. Public education and preparedness. Public awareness and education about earthquake preparedness and safety measures are crucial to minimize injuries and casualties during seismic event. Government regulations and building codes. Government agencies plays a critical role in enforcing seismic safety regulations and building codes to ensure that new constructions and retrofitting projects comply with seismic safety standards. Seismic safety is a complex and multifaceted aspect of civil engineering and construction. It requires a comprehensive approach that includes proper design, construction, retrofitting and ongoing maintenance to reduce the risk of damage and protect lives and property during earthquakes. Safety in designs. Safety in design, architecture and engineers must consider safety in the initial design phase. This includes designing structures with proper ingress and egress routes accessible to all and incorporating safety features like guardrails, handrails and non-slip surfaces. Safety in design, also known as design safety or safety by design, is a fundamental concept in civil engineering and construction that focuses on incorporating safety measures and consideration into the design phase of civil structures. This proactive approach aims to identify and mitigate potential hazards, reduce risk and enhance overall safety of a building or infrastructure project. Here are key aspects of safety in design in civil structures. Hazardous identification. During the design phase, engineers and architects identify potential hazards that may arise during construction, operation, maintenance and even demolition of the structure. Hazards can include fall risk, electrical hazards, chemical exposure and more. Risk assessment. After identifying hazards, a risk assessment is conducted to evaluate the livelihood and severity of accidents or incidents associated with each hazard. This assessment helps prioritize safety measures. Compliance with codes and standards. Designer must adhere to local building codes, regulations and industry safety standards related to safety. These standards often provide specific guidelines for aspects such as structural safety, fire safety, accessibility and more. Incorporation of safety features. Safety features and system are integrated into the design to minimize risk. Example include guardrails, handrails, fall protection systems, fire sprinklers, emergency lighting and safety signs. Accessibility. Civil structures should be designed to be accessible to all individuals, including those with disabilities. This includes incorporating features like ramps, elevators, wider doorways and braille signage. Escape routes. Safe and well defined escape routes and evacuation plans are designed into buildings to ensure that occupants can quickly and safely exit in case of emergencies such as fires or earthquakes. Structural integrity. Ensuring the structural integrity of the design is essential for safety. The design must consider the structure ability to withstand environmental forces such as winds, snow and earthquakes to prevent collapse. Material selection. The choice of construction materials should take into the account factors like fire resistance, durability and non-toxicity to enhance safety. Fire safety. Designers incorporate fire resistant materials, fire detection systems, fire suppression systems, example sprinklers and fire exits to minimize the risks of fire related accidents. Occupational safety. Safety in design extends to the safety of construction workers. Designers must consider the safety of workers during construction, including the prevention of falls, exposure to hazardous materials and safe access to work areas. Maintenance considerations. The ease of maintenance and inspection should be considered in the design to ensure that safety features and structural elements can be regularly checked and maintained. Environmental safety. Designers may also consider environmental safety by incorporating sustainable and eco-friendly features such as energy efficient systems, pollution control measures and green building practices. Emergency response systems. Civil structure may include system for emergency response coordination such as fire alarm systems, security systems and communication equipment to facilitate prompt responses to emergencies. Safety documentation. Comprehensive safety documentation including safety plans, maintenance procedures and emergency response protocols should be part of the design package. Continuous safety assessment. Safety in design in an iterative process that involves ongoing evaluations and refinement of safety measures as the project progress and as new information becomes available. By integrating safety consideration into the design phases of civil structures, potential hazards and risks can be identified and addressed early in the project, reducing the likelihood of accidents and incidents during construction and throughout the life of the structure. The proactive approach contributes to the overall safety and well-being of occupants, users and the public. Electrical safety. Electrical safety, proper electrical design and installation are crucial to prevent electrical hazards such as short circuits, electrical fires and electrocution. Electrical system should be inspected and maintained regularly. Plumbing and gas safety. Plumbing and gas safety. Plumbing and gas system should be installed and maintained to prevent leaks, which can lead to structural damage or health hazards. Gas systems should also incorporate safety features like automatic shut-off valves. Ventilation and indoor air quality. Ventilation and indoor air quality. Adequate ventilation is necessary to maintain indoor air quality and prevent the buildup of pollutants and toxins. Proper HVAC system and air quality monitoring can help ensure occupants' safety and health. Accessibility. Accessibility. Civil structure should be designed to be accessible to all, including individuals with disabilities. This include features like ramps, elevators and wider doorways to accommodate wheelchairs. Maintenance and inspection. Maintenance and inspection. Regular maintenance and inspection are essential to identify and address potential safety hazards. This includes checking for structural deterioration, electrical faults, plumbing leak and other issues that could compromise safety. Maintenance and inspection are critical aspects of ensuring the long term safety. functionality and durability of civil structures. Proper and regular maintenance along with through inspections can help identify issues early, prevent structural deterioration and extend the lifespan of buildings. Bridges, roads and other infrastructures. Here are key considerations for maintenance and inspection in civil structures. Scheduled maintenance. Civil structure should have a planned and scheduled maintenance program that includes routine, preventive and predictive maintenance activities. This program outlines the task schedules and responsible parties for maintenance. Routine maintenance. Routine maintenance includes regular tasks such as cleaning, lubricating moving parts, checking fluid levels and replacing worn components. It helps prevent minor issues from escalating into major problem. Preventive maintenance. Preventive maintenance includes scheduled inspections and maintenance activities aimed at preventing common structural and equipment failures. Examples include repainting to protect against corrosion and replacing weathered seals to prevent water infiltration. Predictive maintenance. Predictive maintenance uses data and monitoring techniques to predict when equipment or structures may fail. For example, sensors can be used to monitor the health of critical structural components and detect signs of deterioration or strain. Safety inspections. Regular safety inspections are conducted to identify and rectify safety hazards. This includes checking for loose handrails, damaged stairs, fire safety systems and ensuring emergency exits are unobstructed. Structural inspections. Structural inspections involve a thorough assessment of a structure's condition including its foundation, load bearing elements and overall integrity. These inspections may be visual, non-destructive or involve testing materials for strength and stability. Bridge inspection. Bridges require specialized inspections due to their critical role in transportation infrastructure. Bridge inspection assesses the condition of bridge components such as piers, abutments, decks and support structures. Road and pavement inspection. Regular inspection of road and pavements identifies surface damage, potholes, cracks and other issues that can lead to safety hazards or deterioration. Maintenance measures may include resurfacing, patching or repaving. Corrosion control. Corrosion is a common issue in civil structures, especially in coastal or industrial areas. Corrosion control measures such as painting, cathodic protection and corrosion resistant coating are essential to prevent structural degradation. Environmental considerations. Environmental factors like weather, temperature variations and exposure to chemicals can affect the structural integrity of civil infrastructure. Inspection and maintenance activities should account for these factors. Emergency repairs. In the event of unforeseen damage or structural issues, emergency repairs may be required to ensure the immediate safety and stability of the structure. Expert consultations. For complex structures or specialized systems, example dams, nuclear facilities, expert consultants and engineers may be brought into to conduct in-depth inspection and provide guidance on maintenance and repairs. Budgeting. Adequate budgeting for maintenance and inspection activities is crucial to ensure that resources are available for necessary repairs and upgrades. Regulatory compliance. Civil structures must comply with local, regional and national regulations regarding maintenance and inspection. Failing to meet regulatory requirements can result in fines or legal liabilities. By prioritizing maintenance and inspection in civil structure, owners and operators can enhance safety, reduce the risk of costly structural failures and extend the operational life of the infrastructure. Regular assessment and proactive maintenance measures are essential components responsible asset and management. Emergency preparedness. Emergency preparedness. Civil structures should have emergency plans in place, including evacuation procedures and emergency exits. Safety equipment like fire extinguishers and first aid kits should be readily accessible. Security. In some cases, civil structures may require security measures to protect against unauthorized access or malicious activities. This can include surveillance system, access control and security personnel. Environmental sustainability. Increasingly, safety in civil structure also encompasses sustainability, including measures to reduce energy consumption, use eco-friendly materials and mitigate the impact on the environment. Environmental sustainability is a vital concept that addresses the responsible stewardship of our planet, resources and ecosystem. It involves making choices and taking actions that minimize harm to the environment, conserve natural resources and prompt long-term ecological balance. Embracing environmental sustainability means adopting practices and policies that reduce carbon emission, limit pollution, protect biodiversity and prioritize renewable energy resources. It also encompasses sustainable land use, responsible consumption and waste reduction. Ultimately, the goal of environmental sustainability is to ensure that current and future generations can enjoy a clean, healthy and thriving planet. It requires a collective efforts from individuals, business, governments and organizations to implement sustainable practices and make choices that benefit both humanity and the natural world. Conclusion. In summary, safety in typical structures involves a holistic approach that encompasses structural integrity, fire safety, earthquake resistance, accessibility, regular maintenance and various other factors to ensure the well-being of occupants and the longevity of the structure. Building codes and regulations play a crucial role in establishing safety standards that must be followed during design and construction. Thank you and have a nice day.